Is a car an investment? Well, in general, no. It depreciates in value each year. As a matter of fact, it depreciates as soon as you buy it and drive it off the lot. Now, if something goes down in value, we say depreciate. If it goes up in value, it appreciates. So let's take a look at what happens to a car's value if, oh yeah, this was back in the day, 2012, we're going back in time. 2012, we buy a new Cadillac and it costs $42,000. We're gonna leave out tax and all that. So in general, how much is my Cadillac gonna be worth in the year 2013? Because remember, we zoom back in time. Let's find out. So we have 42,000 and it's going to depreciate by 15% yearly. Now, do we put 15% in an equation? No, we have to go decimal form. So 15% means per 100. That means we're dividing by 100. So it always moves the decimal place 2 places to the left. So it becomes 0.15. Here we go. 42,000, and I'm going to multiply it by 15%, so 0.15. Well, that gives me 6,300. That's how much value I will lose in the first year from 2012 to 2013. Okay, so then what's my car worth after the first year? Well, then I have to take 42,000 and subtract 6,300. All right, what about in 2014? I'm at $35,700 right now. Does it depreciate another 6,300? No, because now it's 15% of the new value. So 35,700 times 15%, then I have to subtract that amount from the 35,700. Let's try. All right, we can continue in this manner and see what it is worth 5 years after 2012, the year it was purchased. But there's probably a better way to go about this. So let's think about what we've done so far. We took the original value multiplied by 0.15, that's 15%, to find out how much it depreciated. Then we had to subtract that amount from the original value. So 42,000, and we subtracted 42,000 times 0.15. So I'm purposefully writing it in this manner because I want you to notice something that ends up happening. So that 42,000 times 0.15. Well, couldn't we factor out 42,000? Yes, let's factor out 42,000, leaving 1 minus 0.15. All right, so 42,000 times 1 minus 0.15. Does that give us the same value, 35,700? You can check it on your calculator. Yes, it does. So another way to think of this is we could have said 42,000 times 0.85 because 1 minus 0.15 is 0.85. All right, but that's still not all I wanted us to notice. What did we do after we got that 35,700? Well, then we took the 35,700 and we subtracted the 15% of the 35,700. So that same idea, what am I going to do? Factor that out, right? And I'm going to have that 1 minus 0.15. Well, then that means all that I'm doing is continually multiplying by 1 minus 0.15. 1 minus 0.15 over and over and over again. So once again, basically I took the 42,000 multiplied by 1 minus 0.15, got the 35,700. Then I took that 35,700 and once again multiplied it by 1 minus 0.15. So with that in mind, are we really saying that I could just say 42,000 times this 1 minus 0.15 or 0.85 times the 1 minus 0.15 again, and that should get me to the 30,345. Yes, it does. So that would mean that I could just simply continue to multiply by powers of 1 minus 0.15. So this would be squared, and that would give me the 30,345. Well, what about if I want the third year now? Well then, 42,000 times 1 minus 0.15 cubed. Let's see what we get. Are you starting to see the pattern? All right, I want you to go ahead, make sure you've grabbed your own calculator and figure out what is it worth after the 4th year and then the 5th year. Come back right after you filled in the table. So after year 5, the $42,000 car is now only worth $18,635.62. See, not an investment. A necessity probably, well maybe not a Cadillac, but a car. Let's write an equation to model the car's depreciation regardless of what year we're in. Alrighty, so let's use V for the car's value and T for time. Time in years. Well, we actually already created the equation. Let's go back over here. We found this value of $25,793.25 because we used that initial car value and multiplied repeatedly by 1 minus 0.15 or 0.85. So we kind of have our equation written for us, right? The value based on time, in this case, it would be after 3 years. So to write our equation that would model at any given year, I'll just say V based on time, the initial value $42,000 times 1 minus 0.15, what? Raised to T, raised to the year that I wanted. So here I had wanted year 3 and I put a 3 up there. So let's keep that in mind. Let's see, 2012, 5 years later. Well, now what is it going to be worth 10 years later? Go ahead and check that really quick. Value of the car when T is 10. Remember, I could replace this with 0.85, especially if I'm going to use it repeatedly. Once again, 1 minus 0.15 is 0.85, and raise it to the 10th power for 10 years. And I get $8,268.72. Let's be sure and put that $sign in front and round to 2 decimal places because that's what our money system is. Let's look at how this graphs out. So we're going to have the horizontal axis represent time, and be sure and say time in years. And we'll just go the 5 years that we found originally, 1, 2, 3, 4, 5. And then the value will be our vertical axis, and that's going to be, let's just say in thousands. For our purposes here then, I'm going to count by tens because 10,000, 20,000, 30,000, 40,000, and so on. And now let's just plot our points approximately. So in year 0, it was 42,000, so just a little bit above that 40. Next, in year 1, it was only worth 35,700, about 36,000. So let's estimate that point. Continue estimating, plot the rest of the points through year 5. Okay, might be better if we had graph paper here, but we can at least hopefully start seeing that this is not a linear association. Our points start tapering off a little bit, and if we just look at those values, we can see that anyways. We don't consistently go down by 6,300 each year. It reduces each year. So let's go ahead and sketch this. It's going to be a smooth curve. It's a little bit more steep to start with, but then it levels off because we start losing less and less value because it's not worth as much each year. So we see that we have graphed V of T equals 42,000 times that 0.85 raised to time T. That is our exponent. The exponent position has the variable. It creates an exponential graph. And in this case, it's an exponential decay because it's decreasing. The general equation for an exponential growth or decay is y equals a times b raised to the x, where a is your initial value and b is your growth or decay factor. Let's talk about that growth or decay factor. We know this one was decreasing, so it has a decay factor. Where did the 0.85 come from? Well, it came from that 1 minus 0.15. We were subtracting that percent decrease, and we got 0.85. One more time, just to emphasize, you might want to get this jotted down. How do we know if it's an exponential equation? When the variable is the exponent. So remember that. Next, let's practice a little bit of what we learned. If we have this y equals a times b to the x, and b is our growth or decay factor, how can I find b given a percent increase or percent decrease? That's the next thing we're going to practice. On part A, it says negative 3%, so a decrease of 3%. So to find b, I'll simply go 1 minus, do I put 3% in there? Nope. What do I have to do? Percent per 100. 3 divided by 100. Bloop, bloop. Move that decimal places 2 places to the left. So 0.03. So 1 minus 0.03 to get 0.97. So it decreased by 3%, and 0.97 is our decay factor. What about letter B? 0.07%. Do we still have to move the decimal? There's a decimal in it, right? Yeah, we do, because percent is still per 100. And then on part C, it just says 4.5%. So that's a percent increase. What are you going to do different? Pause the video, try B and C, come back and check with me. Okay, that percent decrease of 0.07%, we had to subtract 0.0007, and our answer is 0.9993. And is that our growth or a decay factor? Decay, because our percent decreased. Look at C now. That was an increase of 4.5%, so we had to add that percent. So 1 plus 0.045, and we get a growth factor. So let's really be specific here. How do I know if it's growth or decay? Well, if it's greater than 1, it's growth, and if it is less than 1, it's decay. Let's check our learning so far. We have a car that's $23,000 to start with. It depreciates by 18% per year. What is it going to be worth in 7 years? So here's the pop quiz. Can you write a model, V of t equals, and write the equation that represents this problem, and then use that equation to find the value after 7 years? Pause the video, give it a try. Let's remember that we want a general model that we can use for multiple problems if needed. So that V of t, 23,000, 1 minus 0.18 raised to the t. Now I went ahead and did the 1 minus 0.18 and got 0.82. That's a little bit easier to work with if I have to type it in repeatedly into a calculator. So with that, after 7 years, I have a car's value of $5,733, and it said 0.565. Now, if we were really going to the penny, I would want every penny possible for this car. So 6, right next to that, is the 5. That means I would round the 6 up to a 7. So I went ahead and took that extra penny, $5,733.57.
Now that we're out of the car, let's gander into the kitchen. You ever wonder what happens when you don't clean your kitchen counters? Let's find out. A certain strain of bacteria is growing on your kitchen counter and doubles every 15 minutes. Gross! Assuming that you start with only 1 bacterium, how many will be present after 2 hours? What do you think? You think it'll just be like 30 bacterium? I mean, it doubles every 15 minutes. Let's see what happens. After no time at all, we have 1 bacterium on the kitchen counter. Okay, after the first 15-minute period, now we've doubled that, so we have 2. Okay, after the second 15-minute increment, we have what? That's 30 minutes, so we've doubled 2, so now that's 4 bacterium. All right. Okay, what's the next 15-minute increment? What, 45 minutes? And we're doubling 4, so now we're at 8. What do you think it's gonna be at 2 hours? How many 15-minute increments is that 2 hours? If 4 15-minute increments fit inside of 1 hour, then I know that 8 fit inside of 2 hours. So I'm on increment 3. Do I really want to do this 5 more times? Ugh, no. I'm noticing that we're repeatedly multiplying by 2. So let's try to use what we did in that first example to come up with a quicker way to figure this out. So we could use y equals a times b to the x, but we're working with bacteria and time here. So let's use b of t, where b is my bacteria and then t is my number of 15-minute increments. Okay, so we've got our initial bacteria on the counter is 1, times, okay, the base. What are we increasing by each time? Well, we're doubling. So 2 to the t power. I want to know how much bacteria I have after 2 hours. So that's going to be b of 8. 1 times 2 to the 8th. What do we think? Well, b of 8 is 256. That's not that bad. After 2 hours, I don't have that much bacteria on my kitchen counter. What about after like 7 hours? Let's use this model we just created. B of t equals 1 times 2 to the t. And let's figure out, okay, 7 hours. So that would be 4 times 7. So it's going to be b of 28. Oh, you guys, this number's insane. 268,435,456 bacteria after 7 hours? That's like I left the kitchen counter in the morning, went to work, and then came back, and I have that much bacteria. Oh, I'm a little grossed out, but let's see what this looks like graphically. Okay, time's gonna be our independent variable, so let's get that on the x-axis and then bacteria on the y. So for my horizontal axis, I'm gonna want 8 tick marks for my 15-minute time increments. And then for my vertical axis, I'm gonna want, let's go by 25s. So that first tick mark at times 0 is gonna be at 1, and then the second one is gonna be at 2, and then the third is gonna be at 4. You get this. Go ahead and plot your points. Wow, take a look at this graph. We really did start off kind of flat, and then all of a sudden it just explodes. Exponentials explode. Graphs like this are called exponential. Remember, our equation was b of t equals 1 times 2 to the t. Let's make sure we understand the parts here. We know the 1 was that initial amount of bacteria, and that base 2, right, was our growth factor. We know it's growth because 2 is greater than 1. So if 2 is our growth factor, I wonder what our percent of increase is with each time increment. So remember before, if we were given the percent increase, we knew that the growth factor was 1 plus the rate in decimal form, right? And if we're given the percent decrease, it's 1 minus the rate in decimal form. Well, if my growth factor is 2, what would my percent increase be? Well, okay, so 2 equals 1 plus r. So if I subtract 1, I'd get 1 equals r, and that's my rate in decimal form. So if I convert that back to a percent, 2 decimal places to the right, that's 100%. That makes sense. I'm doubling, so I'm increasing by 100% each time. So we went from 1 bacterium, and then after 2 hours, we had 256 bacterium. Really didn't seem all that bad, but then we figured out after 7 hours, it just explodes into a massive amount of bacterium. What if we started with a different amount of bacteria, like 150? How would your equation change? Well, my A value would change because that's my initial value. So now I would have B of t equals 150 times 2 to the t. Okay, well then we could figure out after 2 hours how much bacteria we'd have by plugging in 8. But we could also figure out after 7 hours. You want to try that one? Let's plug in 28. Holy moly. We got a number so big, our calculator can't even tell us what it is without using scientific notation. This is calculator speak for scientific notation. We are never, ever gonna write that E down like that on our paper. This was your one and only time to do that. So what this actually means is we're taking that decimal 4.026 and so on, and we're multiplying it by 10 to the power specified, 10. So this is gonna be so ginormous because I'm gonna grab this decimal and I'm gonna move it to the right 10 places. Oh my gosh, do we even know how to say a number this big? Let's try. 65,318,400 bacteria after 7 hours. Clean your counters!
We've learned so much about exponential growth and decay, and now we're ready to tackle a few different types of problems. So we know how to get our growth factor or decay factor if we're given a percent increase or decrease, but that's not always how problems present. So take a look at our last problem. We have a population that is projected to grow exponentially for 15 years. In 2010, the population was 3,000, but then in 2011, it's 3,115. what is the population going to be in 2015? Whew, that's a lot to unpack. Let's just start here. We need to find the growth factor. It is growing exponentially, and we're given 2 data points, so that's good. We need to figure out what b is. We know we have this equation, y equals a times b to the x. I know my initial. What's our initial? Well, in 2010, we had 3,000, so a is going to be 3,000. B is the problem here. I'm not told that it's growing by a certain percent, so I have to figure that out myself. I have to figure out that growth factor. To find the growth factor B, I always take the term and divide by the previous term. What do I mean by that? Well, we're given information in 2011, we had 3,115, so I'm going to take that number and divide it by the previous, which is 3,000. Please get that stuck in your head. You always divide by the previous. When I divide that, I get this 1.038 and more digits. But for our purposes, we're going to go ahead and chop it off after 3 decimal places. We don't want to chop it off too small or we'll lose accuracy. To be more accurate, I would write out even more decimal places. Or I could just keep it in fraction form until I plug it in. Let's write a general model for this problem that we can use to find the population in any year, and then we'll use it to solve for the year that we were asked. So it's population. Let's use P for population and T for time. What's our initial? Now don't use the 3,115, right? That wasn't the initial. The first data point I was given was 3,000. And then times our growth factor. So here I can put the 1.038, or if I wanted to keep a lot of accuracy, I could just put that fraction in there. So now we have our general equation. I chose to keep the fraction because that's going to give me the most accurate answer, but you would be fine to go ahead and put the decimal in there so long as you have enough decimal places. Now, we're asked for the population in 2015. What was our initial year? 2010. So 2015, 5 years later. So we'll plug in 5 for T and solve. So we use these models at times to project population, but in reality, any population would have a limit. So it might start exponential, but it won't grow without bound. It'll eventually level off again. That's a different function we don't have to talk about yet.